We think so.
Okay. Well, I hope that you got the. Let me share my screen. And I hope that you realize that what I was missing to make it explicit was that when we consider a Coulomb failure criterion, and we have a sort of a cohesion when the material is intact, and when we have friction, the slope of the line of the envelope is not zero, it's something. And that something is creating an angle of fracture that is going nearer to the principal axis, stress principal axis, so sigma 1. So it's not 45, it's a little bit less. It depends on friction. And the solution, okay, again, let me share my screen. Let me share all of it. Okay, and the explicit solution was here, exactly here. Because this angle here depends on the slope of a Coulomb envelope. And that slope is not zero for real materials. That's why the fracture angle is going nearer to sigma 1. Or if you want, the normal of the fracture plane is going far from sigma 2, whatever. So that was the solution to the conceptual homework that I assigned to you. And okay, the general summary was the Anderson theory of faulting, that is just considering that one of the principal stresses in the Earth, starting from a self-gravitating equilibrium, so the vertical axis, or if you want the radial axis in a spherical reference, is one of the principal axes. So we have three possibilities. It's the minimum, it's the largest, it's the intermediate. And we have these three main tectonic conditions. So extensionals, normal faulting, compressional, so you have a thrust faulting, and intermediate, and we have a sort of a strike slip faulting. So this is the dynamic framework. And we also discovered that the tectonic conditions is causing, at the beginning of the history, the fracture planes, then it is more favorable to continue the slipping over an existing fracture in general. And so dynamically, we understand that we can slip behavior. And that's the summary if you want. So we can describe a fault plane using a strike angle, a dip angle, and that's the fault, plus a third angle that is telling us what is the relative motion of one block, the hanging wall, respect to the other one, the foot wall. And we have a slip. So that's our dynamic framework. What we are supposed to do today is to look within this dynamic framework and try to solve the problem, the elastodynamic problem, from a kinematic point of view. What does it mean is that we are going to forget about dynamics and we want to make a description of what's going on when we have a rupture. The problem is not easy. And actually the solution that was coming around the mid-60s, first from Japan, and then from US, thanks to Leon Nopov and Robert Burridge, and they formulated on a beautiful paper the representation theorem that was the answer to a quite a long debate. And the question is, okay, given a fault, given a rupture on the fault, how can we represent it? Represent it means that, okay, we're going to replace the fault and we want to put some actors to be found that we can handle, because we cannot analytically treat the slip on the fold. You know why? Because it's a discontinuity. In what? In the displacement field, because we have a slip. So if you want, we can translate this problem in a sort of analytical problem, how to solve the equations of motion, elastodynamic equations of motion, with a discontinuity. We cannot, but we can represent it. And the solution at the end, my friends, is a very simple one, but only at the end. So the representation theorem that we're going to discuss today is a very powerful tool, maybe the most powerful in seismic source theory. And at the end of the story, at the end of the path, we will have a very simple answer. But please remember that this answer is valid when we assume some conditions. And the strongest and the easiest one will be the point source approximation. If we consider a point source approximation, well, the representation theorem is saying us, okay, forget about the fold and take a double couple. Okay, something like that.
Okay. Sorry, Professor, are you sharing new slides?
Not yet. Not yet. I'm still in the faulting summary. Now I'm going to close this lecture. And that's the new one. It's beautiful, isn't it? Okay, let me start from the beginning. That's the beginning. Now, this is the path that we have to walk today. It's a beautiful and terrific path because it's going to involve a lot of expressions. But let me tell you, and I hope it's a clear message from me to you, we are going to see today a lot of formulas. I don't care if you, well, it's not important for me that you remember all of them. I don't. I need the slides to, well, I remember because it's pretty much 20 years that I'm showing this, but what I really care is that we do understand the steps logically. So, message, we're going to navigate through elastodynamic theorems today. Unicity, reciprocity, elastodynamic, that's the most important concept of the Green's function. And we're going to open a lecture about that on Monday. And then representation. But the key concept here is that we're going to find equivalent body forces to a shear dislocation. And we're going to introduce maybe the most important concept, that is moment tensor. Inside the moment tensor, we're going to find a skeleton corresponding to a double couple and a scalar quantity that we're going to call the seismic moment. And the seismic moment is one of the messages to take home, and you definitely have to remember it. Necessary condition to pass the exam, but not sufficient, is to understand scalar moment, M0. I've been writing it during the last lecture. Oh, one of the homework to you was to, okay, try to solve for its units. Let me try. Okay, this equilibrium is a little bit unstable, but I hope I'm going to survive. Oh, it's not going through. Let's see if I can erase this. Okay. Scalar moment, rigidity modulus, the area of the rupture, average slip. That's the end of the story for today. Oh. That's today's end of the story. But I was asking you to find the units of this simple quantity. Well, let me tell you, the units are the units of a moment. Because rigidity modulus is an elastic constant. Oh, well, it's an elastic parameter. So the units are force over area. Times an area makes a force, times a slip makes Newton times meters as units. It's a moment. Now you should ask, a moment of what? Well, it will be the moment of a force, of a couple of forces. And we will get to. That's the end of the story. So let's keep it in mind, because using this quantity, Kanamori in 1977 created a new version of magnitude. It's called moment magnitude. And it's using this quantity here. So when you're hearing the news about an earthquake with a given magnitude, and unfortunately, it happens, the number that you're going to listen most of the time is no more the Richter magnitude as Charles Richter defined in 1933 with a beautiful idea and very simple. We will study it in one slide, but actually it's referring to moment magnitude. Okay, that's the plan. That's the roadmap. Can we start? Okay, let's start from a nice picture. Is it working? Oh, okay. A nice picture with beautiful colors here that I was grabbing from a paper that appeared after the March 2011 Tohoku event to show you how people is using what we're going to discuss today and producing beautiful scientific papers about kinematic models of an earthquake. And since we had been using the Tohoku event as a sort of a skeleton, conceptual skeleton of this course, this is one of the results. So it's just an example. But what we do see here is that on the left panel, for example, okay, there are two models, so top and bottom. Let's focus just on the top. What you see on the left is the distribution of slip over a model of a fault plane or surface for that event. What we do see here is slip in meters. What we do see here are beautiful colored, red colored patches. So huge slip, less slip, no more slip. These lines here are timelines, isochrones, because the rupture was starting, spreading, leaving, stopping. So slip in time and space. How to perform this sort of inversion? Well, with representation theorem. So, message to take home. What we can study when an earthquake occurs is the radiation. From a seismological point of view, what we study are seismic waves. Of course, we can combine this information with additional one, and very important one, like GPS. And this is a reminder to Alessandra Borghi's course. But if we study the seismic radiation, we get a signature of a rupture that occurred somewhere. And the rupture means, okay, we have a slip vector field in direction and amplitude that could be variable in space and time. What to do next? Okay, we can make an average. And an average, from an analytical point of view, is something that is like an integral. So we are going to perform an integral over the fault plane of a slip vector field. And we can create an average. And this step here, I know it's an old-fashioned cartoon here, but it's important. Well, now we have an average dislocation model with one arrow pointing in one direction with a given amplitude. And when we perform this average here, we are now squeezing all the time information of the rupture that we are no more trying to understand why dynamically occurred, but we want to describe how kinematically it evolved. Now, all the time information is squeezed, and we are left with just one time parameter, that is the time necessary to the slip to occur on average. We will call that rise time. It's an important kinematic parameter. It will be this time here. And then what we can do using this average will make, okay, let's forget about dislocation. Let's take a representative. And the representative will be a double couple.
A double, sorry, Professor, can you repeat?
Double couple.
Thank you.
Double couple. You will see it in the next slide. Well, you will read it in the next slide. But that's the idea. You take the fault, its kinematics, to describe it, to represent it. Is it clear? You could ask why. Well, because we can handle this in the elastodynamic equations. We cannot handle this. We cannot. And you will understand why. Okay, a piece of history here. The first paper solving the debate and the theoretical problem had been published in 1963, but in Japanese. And okay, that's the translation of the title, on the force equivalence. 1 year later, Leonopov and Bob Burridge published a very seminal paper, so seminal that it has been, well, let me tell you, in many seismology courses, this is skipped because it's too complicated. So just the idea, okay, here you have a double couple, let's go on. No, I want we to go together through this beautiful paper. Now look at the title, Body Force Equivalence for Seismic Dislocations. And this is a picture of Leonopov. Leonopov visited ICTP many times in the past. He was one of the, I think, most important seismologists because he studied the source, he studied the propagation, he studied pretty much everything, acoustics, whatever. And he performed in many lectures when I was a student, sorry for you guys, at ICTP. And he was also a very good teacher, a magnificent one. By the way, this is the abstract that I was grabbing from the paper. Explicit expression, dislocation, and look at the final statement. For displacement, dislocation, faults, what does it mean? A tectonic event where you don't have opening or explosions. That's a different story. Well, a representation theorem can be used also in that case, but here they are referring to a shear dislocation. So a tectonic movement, stick and slip. The double couple is an exact equivalent body force. Now, it's an equivalent. Don't think that we have double couples inside the Earth. We have ruptures inside the Earth, but we can represent them. So it's an equivalent, and we can use that. That's the picture. And as I was telling you, the picture is so important that José Pujol later, and quite recently, published on Seismological Research Letters a tutorial, because it's considered really a tough paper, that one. And so I was grabbing from Jose paper also these statements. And it's nice because Seismological SSR republished again the note of paper with a tutorial just to highlight how important that paper is. There is something nice here, since now you're staying in Italy, you're listening to some Italian, and there is an Italian story here, because one of the first scientists to study fractures and what we call now dislocations, the dislocation was shear dislocation was used by Love. You have the same Love that studied the Love waves. But actually it was starting from Italian, and Vito Volterra, he was a mathematician, a very famous one. Actually, he was using the Italian word distorsione. That means something that is shearing some material. And so Sir Love decided to translate this into dislocation. So the term dislocation has a long story. And there was a debate after the starting of instrumental seismology, that is quite a new, well, relatively new field, because the first recording, we will see it together in some lectures. Well, actually, it had been recorded only in 1906. So let's say we have 100 years of instrumental seismology. Seismology before was a theoretical field, and all the beautiful mathematicians were taking part to it, from Lagrange, from, you can think whatever, Lagrange, Fourier, Euler, whatever. But then in the 60s, there was a theoretical debate using recordings. Okay, what is the best representative of a shear dislocation? Some people were saying, okay, a force. Let's take the simplest one. No, it's not working. Well, let's take a couple, so that for an internal source, we have a force balance. Well, but if you have a couple, you have a rotation. So someone was saying, no, wait, it should be at least a double couple. But there was a debate. You know why? Because from the radiation field of P waves, there is no way to distinguish between a couple and a double couple. So there was a debate, and the debate ended. Just, let's say, approximately 50 years ago. Oh, well, 70. I'm getting older. By the way, so it's an important issue, what we're going to do. And this is the path that we're going to take. It's a terrible one. Now, let's start training within this path. And I really hope, and my hope is a beautiful hope, that you studied the equations of elastic motion in wave physics, or for you, Aurora, in other courses. The equations of elastic motion can be summarized like this. Well, what do we have here? Newton. F is equal to ma. So you can use it instead for a material point, you can use it for a volume, you can use it for fluid dynamics, and you will get Navier-Stokes equations. But for solid mechanics, that's it. F is equal ma, so density, acceleration. And here we have the spatial derivative of a stress tensor. It's so simple. Of course, this is the starting point, because then you're going to assume, okay, we do have a homogeneous universe. You can write the stress in terms of strain. You can put there lambda mu, and you get the beautiful equations of P waves, S waves, Rayleigh waves with boundary conditions, Love waves with layering, whatever. And you can solve it also in a spherical system of coordinates, and you can study the three modes of the Earth. So this is the most general writing and pure writing of elastodynamic equations of motion. And we can define an elastodynamic operator Please do remember that this is a vector and I'm using the Einstein notation of repeated index. If an index is repeated, there is a sum here. Okay? Please do remember that you're part of a PhD program, advanced, theoretical one, and part of a diploma course at ICTP, International Center of Theoretical Physics. So Einstein notation should be in your pocket. So JJ means repeated index, but there is a sum, implicit sum there. It's just a thin way to write the equations of motion. Okay, if you want to be more elegant, you can rewrite this equation using this operator. You take minus here, and that's it. Now, wait a second. When the inhomogeneous term f is 0, we have a normal equations of motion without any external action. And we can solve it. We can find p waves, s waves, whatever. 1D, 2D, 3D, whatever. So that's the homogeneous version of the elastodynamic problem. Solved it. Well, when I was doing wave physics course, many examples of solutions. You can also have here the acoustic waves. Everything depends on the, how to say, constitutive relations. Of course, usually, well, let's say pretty much always, what we use here is the Hooke's law. Stress can be written in terms of strain. Strain can be written in terms of displacement, and we can find the equations of motion for p waves, s waves, Rayleigh waves, love waves, whatever. Do we agree upon this point? It's a question. So we are relaxed here. Good. Now, what about VF? Because now something is getting more complicated. Okay, let's see. Let me try for 1 second. Okay, I'm going to lose time, but it's at your favor, I hope. So let me try to stop sharing for 1 second. Where is it? Stop sharing. So you can see this is, okay, let me try to, I have to use alcohol here. Okay, let me try to write one equation. You should recognize it. It's the harmonic oscillator equation. You can get the beautiful solution of the pendulum. Okay, you studied it. If not, you're not the same people of the previous courses. Now, when this is 0, that's easy. And you get a beautiful harmonic solution. Now, what about the situation in which that's not 0 and you have a forcing outside? Someone is pushing you, for example, on a spring, on a swing, sorry. Have you studied this problem? It's called the inhomogeneous version of a differential equation. For example, you can study it and calling it the forced harmonic oscillator. It's an example of an inhomogeneous differential equation. And in some cases, it's not easy. But there is a way to solve it. And we are going to use this way in one of the next lectures. For example, what you can do is to consider the forcing as a delta. And you can study this, and maybe you can solve it. And how do you call this? Well, in systems theory, many people is calling it the impulse response. And if you take the Fourier transform of this problem, you can call it the transfer function. But if you're a mathematician, you're going to call the solution of the inhomogeneous problem when the non-homogeneous term is a delta, you're going to call it the Green's function. Okay, so maybe we can go back to our elastodynamic problem and consider the inhomogeneous term as a delta. But wait a second, a delta of what? Well, when we have the harmonic oscillator, we have just one variable, it's time. So that's an impulse in time. It's like if you have a friend on a swing and you give a kick. Or you take a pendulum, okay, I don't want to crash my whiteboard, but okay, if we, let's imagine to be each us in front, in a beautiful world with no pandemia, I would play a sort of a game with with a sort of a string and I'm going to force an oscillator. Usually I was doing that in room H using a stick that usually is there. And okay, if I was forcing it, we would admire the response of the system in terms of a forced oscillation. Who is the forcing? That's me, in principle. Let's take a building. Let's study the force oscillation of the building. Who is the forcing? The ground motion related to an earthquake. And you have many examples. But here, we have just one variable, time. For the elastodynamic problem, we have much more variables because we have 4. We have 3 spatial and 1 in time. So let me share again. And let's give a look to it again. Remember that what we are looking for is the solution in terms of u, that's the displacement. And u, in this very synthetic expression, is a function of space and time. So a question to you now. Let's imagine that this f here is a delta. Which kind of delta will have to be? Any idea? Please feel free to say whatever. Here we are to understand things. Are you there? Okay. Let's cut the story short. The delta should be a delta in time, a delta in space, because we have to create an impulse somewhere in space at a given point in time, and that will be the messy part. We have also to establish a direction. Because for us, it will not be enough to study the acoustic problem. You know what is the acoustic problem? a delta in time and space, and that's enough. And you can call it the acoustic Green's function. Do you want an example? Okay, what you heard, okay, after some transfer, thanks Fourier, Wi-Fi, getting to your rooms, and you had been listening to the reverberation and the Green's function in my poor room. So a delta in time, a delta in space, and you can clap in your rooms. Well, don't do it, otherwise some people can think that they're getting crazy. But according to the position of the clapping, according to the position of the microphone, you're going to record the Green's function for a delta somewhere in some time recorded in some place. In my case, I'm clapping here. The microphone is the microphone of my poor Mac here, and that's the recording. But wait a second, for a solid, it's not enough. What we have to add is that we have to establish a delta in time, in space, and in direction. Because we can push, let's imagine to consider our table. Each of us has a table, I hope, that you're using now, and you can imagine to apply a force. You have many ways to apply a force, many directions, many, but in principle, you have 3 orthogonal directions that you can use: vertical, horizontal, horizontal. And let's imagine that we are together in a room. Let's use our imagination. If we were in a room, we would play a game in which we could use a table, we could use an accelerometer that every smartphone has. And until 1 year ago, I was showing the acceleration that you can record, pushing the table from one side, from the other side, from vertical, and you would get 3 different responses. So let's remember that our task for the Green's function, so the solution of this problem when f is a delta in time, in space, and direction, it will be tough. For today, we are just going to define it, and we will call it the Green's function. We're not going to find it too much. We will start to do it from Monday. But please remember that that's the starting point. Elastodynamic equations of motion. Now, okay, let's take a 10 seconds break. Are you with me? Not physically, unfortunately, because you are in your rooms.
Yes, we are.
Are you still following me?
Yes.
Okay.
Yes.
Okay, if not, please stop me. Not for algebra, it will be a mess, but for logic, just for logic. Okay, what we have to do now is to use this basic dynamics equation, Newton, if you want, plus Hooke's, plus contribution, plus Lagrange, Euler, whatever, because stress, Hooke's law, stress and strain, whatever, and try to deal with this problem for our necessity. What is our purpose? Well, to study the problem when the external actor, but actually it will be an internal source, is an earthquake. And we have to find a way out. Actually, our real task is to get U, vector U, that is the solution of the motion, given an earthquake. Okay? That's our target. That's the top of the hill, the top of the mountain, the top of K2, the top of, no, K2 is too difficult. Let's say Everest, something like that. And we have to try to go there. it's a long way. We'll try to take it. Step one. Let's use some basic elastodynamic theorems. The first one, again, I will go fast here, but just to have a logic. I don't want your memory. I want your comprehension of a problem. The first piece that we need is that, okay, if we are doing something, it should be useful. So that the solution has to be unique. Otherwise, we are lost. If it is not unique, okay, let's go, well, let's go nowhere because we can't go anywhere. But, okay, let's look at a movie. What is just saying the uniqueness theorem? Well, in a very short words, is saying, okay, the displacement field that you're looking for, U vector as a function of space and time, will be uniquely determined after initial and boundary conditions. That's the how to say, the short message here. So if you write the initial values of displacement and velocities, please remember the simple problem of the harmonic oscillator. You have always to establish initial conditions if you want to find a solution. What's next? Okay, if you have an elastic body, you have to establish what are the body forces there. Now I'm speaking not about representative body forces, I'm speaking about real body forces. One example is, and maybe it's the most important for the Earth system, is gravity. Gravity is a body force. Elastic forces are not body forces, they are surface forces. So gravity is given. You want another magnetic force, but we're not studying plasmas here. So, okay, let's say you establish the body forces in your body, it's the Earth. The amount of energy in your body, that's the Earth. In every point of your elastic body, the Earth, you can establish for every surface, internal, also traction, so surface forces. Now, if you're looking for a solution, that will be unique. Good to know, we can go. So I'm not going to demonstrate. There is all the pieces are in Aki and Richards, but I don't care about them. I care about logic. So with this theorem, we can go on. It's a gate. Then the second one. And now it's becoming funny. And you could ask, okay, who cares about this theorem? Because we want to study something else. But this theorem that is called, in many cases, reciprocity theorem is saying, okay, now let's imagine that you have two solutions. One solution for a given problem. So given problem means given initial conditions and given body forces and surface forces, and you have one solution. So U given F. Then you have another one. It's V given another body force system. Well, if you apply the boundary conditions, those two solutions are not independent. They have to obey a sort of a relationship theorem that is called reciprocity due to its symmetry. Because F and U appears here, and V appears here. This is the tractions given the first body force, and these are the tractions given the second body forces. So this is saying that you are taking the integral of volume around the volume that you're studying, the integral about the surfaces that you're studying. These two solutions are not independent. Now let me make a 10 seconds pause here, just to wake you up. Now you should ask me, who cares about this second theorem? Is it useful? Well, the answer is yes, otherwise it would be a terrible slide to throw it away. Let me try to make a sketch. Let me try to make an experiment here. Let's see if my whiteboard is working, and if my poor old iPad, so I don't have an Apple Pencil, a sophisticated one, but I'm going to use, let's see if I'm sharing this. And let's see if I'm sharing this. Do you see it? Do you see a white panel? Okay. Let's hope that this old pen is going to work. Seems not. Oh my goodness. What I'm doing here. It's not working. Huh. Let's see. Okay. Let's take an elastic body with a given volume V. And it has a boundary conditions over all the possible surfaces. And let's imagine to take a cut over it. In this cut, we're going to have the slip. That's the fault. So actually, what we want to study is that, let's imagine now to take that line there, and let's imagine it is a fault. That plane seen from with a rupture that is starting from one point, propagating, propagating, propagating. Here we have a slip, and this is what we want to study. And so we have an elastic body with a given volume, with given elastic parameters, with given boundary conditions. For example, this is a free surface. So what we have around here, it's a free surface. And now we have an additional surface where we have a discontinuity of slip. This is what we want to study. So actually, since we're going to look for U vector due to this problem, one of the solutions that we're looking for has to be this one. Now, how to use the reciprocity theorem? Well, the trick will be that the second solution will be assumed to be a known one. Which one? Well, the solution V, small v, this is volume. The small v solution that we're going to use here, and it's a vector. Oops, it's not going to write. That's a vector. Well, the v that we are going to use will be the Green's function. That's the trick of the representation theorem. So just to sum up what we have been done until now was, okay, we have a uniqueness theorem. We have a reciprocity theorem that is saying, okay, if you have two solutions applied to the same elastic body due to different set of body forces, they are not independent. They have to obey this relation. This is the first form of the reciprocity theorem that is very powerful. For example, some of you spend time with the course with Lapo-Boschi. Lapo is using this theorem here with some unbelievable applications also in acoustics. So it seems very cool in the sense of something unuseful, but actually it is very useful. Let me make a further step, a formal step, but this is a new version of the reciprocity theorem, just rewritten with some time dependencies. Because now we have to imagine a time and a retarded time. You could ask, why do we need this?
Excuse me.
Yes.
So I'm not getting well when you are saying that U and V are independent. Are you trying to mean that
No.
Superposition?
No. Maybe I was not clear in telling. Let me stop sharing and let's take a discussion here. No, I was not saying that they are independent. They are dependent because we are entangled using a sort of the quantum mechanics word by reciprocity theorem. So what I was saying, let me say better, I hope, is that if you have solution U and solution V for the same elastic body, the Earth, they are not independent because they are entangled by reciprocity theorem. This is what I was trying to say. Let me add also one other thing as a sort of an answer. At this point of a step through the reciprocity theorem, all these theorems here appear, how to say, unuseful. So very formal and not dealing with the real problem. My hope, but after 20 years, my guess should be okay. I'm guessing that in continuing with the lecture and considering at the end of the lecture, maybe on Monday, because now we are beginning to run short of time, with a specific example, all these things here will be much more simple and familiar. Remember, now we are at the process of a step that is full of fog. But so we're just looking at the formal pieces now. Is it clear what I'm saying? Innocent? Are you there? So I was getting a question. I was trying to make an answer, but no reply. Do you hear me? The others are copying me?
Yes.
Okay.
Yes.
Yes.
So,
Yes.
okay. So, have I replied temporarily to the question? Okay. Let me try to go on. I told you it's a tough part. Now, and again, let me tell you, just to relax you, I'm not going to ask you the details of the algebra here, just the idea. So this is another way to rewrite reciprocity theorem. Now, what I was saying here is that U and V, the solutions of the same elastodynamic body, but with different body forces, G and F, are not independent. They have to obey this relationship expression. You can call it reciprocity theorem. And now, as I was telling you, we are going to use one of these solutions as a known one. Which one? The Green's function. And now a small digression through the general definition of the Green's function. I'm sure, and I know that Lapo already defined it during the wave physics course. But if not, here you will find its definition from scratch. Every time that you have a linear differential equation, whatever, the harmonic oscillator, so the pendulum, this mass and spring, the wave equation, whatever, and you have a linear differential operator applied to a vector. In the simplest case, we have just a dependency upon one variable, could be time, could be one in space, whatever. And you have to solve the inhomogeneous problem. Well, you can define the Green's function of this problem as the solution when F is a delta. What does it mean? This, I'm clapping my hand in my room at a position S, and you're recording it at a position X. Now you could say, is it useful? Yes. And you're using it every time not when you're listening to music, that's Fourier theorem, but when, for example, you are filtering a picture, because it's at the base of every linear system in time and space. So when you're using, I'm not using, but when you use a sort of a filtering algorithm for pictures, or to create MP3 from a WAV file, actually you're using this definition. By the way, this is a definition. The Green's function is called the solution of a problem when the inhomogeneous term, the heterogeneous term, is a delta. But you could ask, who cares? Well, it's important, because if you know it, you can solve the general problem. And the proof, the simple one, is in the next slide that is going to appear. Because if you take this equation here, you multiply it on both sides by, yes?
Can I call delta, delta is the Dirac function, is that right?
Well, okay, if you want to be more sophisticated, you can call the Dirac function. It's actually what I'm saying as delta. I'm implicitly using the delta of Dirac. You know, in jargon, it's called simply delta, but it's Dirac's delta. For people in algebra, it's called the Kronecker delta or Kronecker operator. And for mathematicians, it's not nice because it's not a function, it's a distribution due to its definition. But thank you, it's the Dirac's delta. So in one variable, it's 0 everywhere except at a point, but the integral is 1. So that's why mathematicians do not like it, and they call it a distribution. If you are in matrix algebra, it's the matrix with all zeros and just ones along the diagonal. If you are a poor theoretical seismologist like myself, I simply call it delta. So it's 0 everywhere except at a point or at a time or along a direction. But thank you. Yes, what I'm calling delta is Dirac's delta. In quantum mechanics, of course, it's referring to the operator of Dirac's delta. Thank you. Okay? Thank you, Doug. Okay, so how to use it? Well, let's multiply f on both sides, and let's take an integral. And using the linearity of the operator, what we can get is the following. So you take the left multiplied by f, the right multiplied by f, but wait a second. Thanks to the properties of a delta, Dirac's delta, this integral here is just f. But wait a second, f is the solution of L of u applied in x. Let's give a look to this side here. It's linear, so we can take it out. But now let's, sorry for the bells ringing here. What is this? By definition is u. Now, let's give a look to it. The solution in the general case is nothing else. If you compare them, this and this, then you get the general solution is the integral of the Green's function times your operator, the heterogeneous term. You know, this is a sophisticated way to name, using Green's function, what usually is called the impulse response. That's why I was adding some slides in the Moodle website, because this concept is used in many cases, like this one. But we will go back when we will speak more about the Green's function. Let's imagine that you have a linear system. And you know that this is linear. You can consider it a differential operator. So it's described by a linear differential operator. And you want to know how to find y given x. And then you say, okay, let's give it a kick and let's study the answer to the kick.
So
this is called...
I can see see, right?
You don't see this?
Yes.
So
I do.
this is L, sorry.
Okay. Okay. Now, okay. Thank you.
I was not moving.
Okay.
Okay, thank you. So this is L, that's the system, that's the input, that's the output. Problem, how to find the output given the input? Well, you should open the box, look inside, and study it. But there is another version. Let's consider the answer of the box to a delta, and we call it H. You can call it impulse response. And you could say, is it useful? Yes, because when you convolve it by X, by any input, you will get your answer. And in systems theory, the impulse response in the Fourier domain is called the transfer function. It's another way to say that if you know the Green's function of the problem, you get the general solution. The problem is to know it. But now we're going to say, okay, we know it. So that's the general definition of the Green's function. And it is valid in quantum mechanics, electrodynamics, every linear system, Sturdy-Liouville systems, fluid dynamics, acoustics, and seismology. That's the general idea. If you're doing communication, if you're studying communication systems, that's called impulse response. In applied geophysics, and the idea, if you use a hammer and you knock somewhere and you get the recording, you're getting the Green's function. Or if I clap my hand in a room, I will get the acoustic Green's function. Now we have a problem. Because our Green's function, and now I'm going to share again my screen. It's this. Oh my goodness. This is the definition of a Green's function. It's the solution of the elastodynamics equations. This is generalized Hooke's law. This is the stress. This is the partial derivative, repeated index summation. When the inhomogeneous term is a delta. But wait, which delta? It has to be a delta in time, a delta in space, and a delta in direction. And what is telling this is that this definition of a Green's function is defining a tensor because you have two indexes. And you could say, how to remember these two indexes? Well, actually, they are easy. Because one index is referring to the components of a vector at the receiver. And remember, we're living in space, so it has to be a vector. Given the second index, that is the direction of the force applied at the source. And if you put them together, you have a second order tensor. Now, and let's make a 10 seconds pause here. This is the definition of elastodynamics Green's function. And it is the solution of our problem when the inhomogeneous term is not zero, is not whatever, is a delta in time, in space. So you're putting somewhere, sometime, a force in direction n. And you're recording it at a position x along direction y1, y2, y3, because it's a vector. Stop sharing. Let's take a breath. Questions? or you're totally fine and we can move on. I told you, today's lecture and the next one will be terrible for you and me, because it's involving so many concepts. But the reward, I hope, at the end will be a beautiful view. Well, not so beautiful maybe, but okay. Jokes apart. Are we lost in the fog, or still we have a rope that we can use to be together? Okay. Okay. Let's try to move and go to the worst passage. Let's stay together. Let's try not to get lost. So in the next slide, that I'm not going to show you, there are some beautiful symmetry relationships of a Green's function. But just to remember it, you can imagine to clap your hand in your room, to listen to it, and then you will have the Green's function of your room. Don't tell anyone, but that's it. Let me tell you that in environmental acoustics, if you want to study the reverberation time of a beautiful concert room, or in an old church like in Notre Dame de Paris, or in Venice, for example, we did some experiments in Venice, maybe you're not using the clapping hands, but you can use a balloon with a needle. In more sophisticated environments, you can have some artificial sources that should be not invasive, but you can do this with special microphones and study the acoustic environment. So I'm not joking. That's the Green's function. Well, not clapping twice, but just one, and recording. You have any information about your environment. Our situation in elastodynamics is more complicated because we have space and time and direction, because we have solid. I'm knocking my table now. Maybe you hear it. Okay? So the slide that I'm skipping, that you can find in your PDF, is a set of symmetry properties of the Green's function. And one is very nice and very intuitive. Let me share my screen. But I'm not making it to appear. These exchanging indexes here are simply saying that if you change the position of the source and the receiver, and if you switch them, the Green's function is the same. It's used also in optics. By the way, yes.
Sorry, Professor. Can you repeat again what you recently said, please?
Okay. What I'm trying to say here is that using special boundary conditions that are not so special because they are called homogeneous. What does it mean? That if your system has boundary conditions applied to displacement or stress, they are called homogeneous boundary conditions, then the Green's function, defined like in the previous page, can satisfy some reciprocity conditions, and you can switch actually the position in space and time of source and receiver, and you get the same. This trick is often used in theoretical optics, but also in theoretical geophysics. That's not my field, but in applied geophysics, you use it every time that you do some processing of seismic sections. And so in the processing, you're using this to exchange the source with the receiver in space and time. What is simply saying this is that G is not changing. So let's put it in another way. If I see you, you see me. So you cannot hide. If a photon is reaching, starting from one point, another point in space and time, but you can imagine to take the receiver point and the photon emitter and switch them, you will get the same. Okay, these symmetry properties will help just in the next part to simplify expressions. Tell me.
Yeah, sorry for the interruption, Professor. So what you're saying is that in the case that we would have a receiver, we can also have information from the source.
Yes, if you want. What I'm trying to say is that, let's imagine that I'm making my experiment, clapping my hands here, and the microphone there. If I reverse space, position of source and receiver, and time, I would get the same Green's function. It's symmetric, it's invariant in space and time, if you want.
Okay.
Okay?
Yes, thank you again.
Now you could say, I was putting here just as a reference because they are going to be needed from the next slide on. But again, I don't want altogether, we as altogether, to get lost in algebra, but just in idea. What we did until now, unicity theorem, reciprocity theorem, definition of the Green's function. Now we are going to use this definition inside the reciprocity theorem to write what we want to obtain in terms of the Green's function. Please do remember that this is not a solution, it's a definition. That's the definition of elastodynamic Green's function. It's the solution of elastodynamic equations when the inhomogeneous term is a delta in space, time, and direction. This is the new part compared to acoustics. So if you're going to speak with people working in acoustics, you could say, haha, we can do much better because our problem is much more complicated than yours, because we have also to specify direction. Now, if you imagine to take a solid, sorry, I'm using this, okay, like this, you have to imagine that when you have a solid, you can push it from here with a delta, or from here, or from here, or whatever direction, but you have 3 independent directions, 1, 2, 3. And the reaction will be different, of course, because it's a solid. While a gas is behaving like an isotropic, and fluids, like water. For example, in ideal fluids, you don't need the stress tensor. Pressure is enough, as you know, and life is easier. But in solids, we need to specify directions. Okay, before the end of, for today, I know this is so tough, but I'm going very slow, relatively slowly. So don't worry, I will not go over the end of a lecture formally, but I want us to be together, because now we have to make the last step. Well, it's not the last, but one of the last important steps. Now, if we use Betti's theorem, using as one of the 2 solutions the Green's function, that is the solution of the problem, when the body force is a delta, now we can obtain from Betti's theorem a representation of the other solution. And what we get is this. What we can read here is how displacement U, our seismogram, that's our seismogram, please don't forget. At a specific point where we put an instrument, or we are going to compute synthetically a signal in time, so that's our seismogram, will be the result of these 3 different terms. These 3 terms are made by 1 volume integral over body forces, but now these are the real body forces, gravity, for example, times an integral over the Green's function and the tractions inside the body, plus it's the last one, but it is the most important in 5 minutes, plus an integral over the source of the discontinuity of a displacement somewhere times the spatial derivative of a Green's function. Now, I know this is terrible. And maybe it's not so evident, but we are just near to the top of the mountain. We cannot see it, but we are very near. And let me go very slowly here, trying to anticipate what's going on next. Because these three terms will collapse, two of them to zero, and we can forget about them. And one will be just the integral over the fold taking care of a discontinuity displacement that is the slip that is here. And the fault is here because this innocent quantity here is nothing else than the normal of the plane where the slip is occurring. And this piece here, that is tricky, but it's the Green's function. It means we have a fold in a room, actually in an elastic body, that is our Earth. And if we solve G, we have it. So the terrible steps that we made allowed us to reach this point here that appears very hard. It seems that we're stuck here. But actually, the top of the mountain is just there. We have just to accommodate some of these terms so that we can move. Okay, this is a sort of a summary of what we did until now, because I'm writing the same expression as before, but without any dependency, just to make it simpler. And the representation theorem is saying us, okay, you're looking for your seismogram, because this course is of theoretical seismology, in an elastic body that has a given volume V, a given Green's function G, it has some body forces F, plus an integral over the surface, all the possible surfaces that you can imagine in your body, where we have the tractions of our body and something that is a displacement discontinuity somewhere on a plane whose normal is this. 10 seconds pause before making one of the last steps. And I want you to see if you are alive and asleep. Are we still together?
Yes, we are.
Connected by a rope?
We think so.
Okay, I know it's tough. It's tough. It's tough. I told you. I was not lying to you. I was not saying, oh, representation theory is beautiful. We can use the beautiful picture of Leonopov, the abstract, that's it. Okay, let me tell you what's going to happen now. The first term, the integral volume, will vanish. You know why? Because I'm lazy and today is Friday. And in seismology, usually we don't care about gravity. If we are in fluid mechanics, then we will need to take care about gravity. It's the main actor in fluids, gravity waves. But in seismology, once you assume that your body is in self-gravitating system, like our Earth, and now we start from that equilibrium, we don't care gravity. It's too tiny compared to elastic forces. Let's imagine, now we are not in presence, but you can imagine each of us has a table in front of us, I hope, or you're using some strange tricks. By the way, let's imagine that we have to study the vibrations of a table due to someone that is knocking over it. We don't care about gravity because we assume that the initial equilibrium is already satisfied with gravity and the pavement, the floor. So we start from the equilibrium, the table in equilibrium under the gravity system. The mechanical vibrations due to elastic forces in our table, actually, gravity is not acting upon them. So the first term will vanish. Hooray, it's Friday. The second term will vanish as well, because the next step is to take the integral over the surfaces and to make it, how to say, computable, or not zero, only where we have discontinuities. And we have two possible discontinuities. The first one is a discontinuity in the stress system. Something like that. Something is opening, something is imploding. That's a discontinuity in the stress. And for tectonic events, we will consider it zero. Only the third term that is going to refer to a discontinuity in displacement is the important one, and that is what we want. So that large expression actually will collapse, keeping just one term where we have a slip over the fault. So let's take these final steps for today. And now, just few words that you can read in a relaxed way about the sources that we want to treat. In the Earth system, we can have many sources, terrific or not, meteorite impacts, atmospheric perturbations over the sea, for example. That's important, but that's, for seismology, it's an external force. Then we want to care about tectonic events. Those are internal sources. So the balance of force should be zero at the end of the story. It's not a meteorite hitting the Earth coming from the space. It's an internal one. And now we have to take care about all the possible internal surfaces and volumes where discontinuities can occur. Okay? In displacement, and this is what we want, or in stress. So actually, the first integral will be neglected, the one in volume, because we will not care about gravity. Sorry to say that, it's a secondary, totally secondary effect compared to elastic forces. The second term could be used, but if you want to study a surface where we have a discontinuity in stress, like someone that is going to open your system or squeeze your system, and we will not use it. But actually, what is going to be left is an integral over the possible surfaces that will be different than zero, only where surface displacement discontinuities will appear, and that's a fault plane. And the fault plane will be described by a versor, a vector, and now I'm going to use, wait a second, let me wake up my iPad and my terrible whiteboard. What's going to happen here? And I want to make a terrible sketch. Okay, let me erase all of it. And let's imagine now, let's see, I hope it is working. Oops. Let's imagine that we have a plane over which we have a discontinuity field in displacement. So we have a dislocation here. Now, how to describe this? Well, if it is a plane, it has only one normal. And we will call it using a unitary vector that is called ni. Sorry, it's not evident, but this is the perpendicular to the plane. So you can imagine that to describe a plane, you just need to specify its normal. if it is a plane. If your surface has more planes, like this one, you will have another one. If you have a complicated surface, over which slip is occurring, your unitary vector will be a function of a coordinate over the fault. But if you have just a plane, it will be a constant. Okay. I was using the Aki and Richards original picture to better describe what's going on here with the original caption. And I added, so I updated the material of your lectures, adding this just for clarity. So now we have to imagine that this potato-like body is the Earth. It has a volume. Body forces are there, but we are starting from an equilibrium. It's surrounded by a free surface, S, that could be one of the principal stress axes. And then we have a place, like a cut in our potato, where displacement is occurring. Not opening, not closing, we have a displacement occurring. And now we have to imagine that along this surface, that we will assume it is a plane described by this normal here, we will have a shear dislocation. So we will have a discontinuity in displacement across this plane here. What is left? What is left then, changing from the previous expression to this one, is, you could say, oh, it's still a mess. What should we do with this? But something was changing here, because the integral over all the surfaces actually is left just here, and the square parentheses here refer to discontinuities. You see here? Discontinuities of what? Well, across a plane defined by, or a surface defined by this vector, and the discontinuity could be in traction, opening, or in displacement, shear dislocation. And the final step will be to kill this term, and focus just on that. Okay, 10 seconds pause. Are you alive and kicking? Are you still there? Yeah, I know it's Friday. Yes. It's a rainy Friday. Everything is terrible today, and the lecture is terrible. But let's try to make the final step. I told you it was a tough one. Now, keyword. In the case of a shear dislocation, what does it mean? Something that is not opening or closing, but just slipping. The tractions across the plane are continuous. So the second term is 0. And neglecting body forces, so the first term, the integral about volume, is 0. We have only the third term. And the third term can be rewritten in many ways. The displacement of the fault actually determines the displacement everywhere. So given the source, we can compute the displacement due to that source. Now, if we want to find an equivalent force to the slip over the fault, we can use this beautiful expression to write the spatial derivative NP. Remember, that's the Green's function. The first term, the first index referred to the coordinate at the receiver. The second one, it's referring to a force pointing somewhere at the source, and this is a spatial derivative along another direction. And if you write this term that is in the third. Like that, you can write what is left in that terrible expression like this. Now you could say, what?
Please, are you sharing the slide?
Oh, it's not. Oh my goodness. I'm speaking. Thank you. So I was speaking with myself. No, well, I was showing this beauty just to myself. I have to share it with you because it's too much beautiful. Again, the real first term of a previous expression goes to zero because we neglect body forces, gravity. The second term is zero because we don't consider traction discontinuities. The third one is left. And we can rewrite the third one using this expression like that, where this term here is this. Now, this is the representation theorem at the most of its power. Because what's telling us is that we can compute the displacement, three components, it's a vector, at a position x of t, where we put our seismometer, as the convolution, tau and t and tau, of the integral over our volume of a body force times the Green's function. Wait a second, this body force is not a real body force. It's not gravity. It's representing a displacement discontinuity on a fold. So what we did, actually, this is the symbolic end of a representation theorem. And this is the representative body force. But still, at this stage, is not, well, it's beautiful, but not for Friday. For Friday, well, we have to digest it. Actually, the digestion will be very quick. And this, under given condition, will become a double couple. By the way, just a short summary, because the representation theorem was saying in its general version that the displacement field at the point of a volume V with the surface S is given by a volume integral over real body forces convolved with the elastodynamic Green's function. But that in practice will be zero. Gravity can be neglected. Then a surface integral over the discontinuity of tractions across a surface convolved with the elastodynamic Green's function. And that will be zero, because we want to study just pure shear dislocations. And then the third term, that is the surface integral over a quantity, depending upon the discontinuity of displacements, that's the slip, convolved with the spatial derivative of the elastodynamic Green's function. So the summary for today's lecture is this: neglecting the physical body forces, gravity, considering a pure shear dislocation, the remaining term can be represented as the result of an equivalent body force. Isn't it beautiful? Okay, it's 12:36. Let me smile because, okay, that was the toughest part of the path, because the next one, let me show it as a prequel, is so nice, but everything is becoming very simple. And to get there, maybe I will need 5 minutes more, and maybe I will take it just to relax, so that we can stay on the top of the hill, maybe enjoying the panoramic view, but understanding it. Now, but before sitting on the top of the hill, let me ask you, I know the algebra is a mess, but concepts should be relatively simple. So we developed a formalism whose aim was to write the displacement field at a point given whatever is happening on the Earth. And whatever means real body forces, let's neglect them. Discontinuities, interactions along some surfaces, we will neglect them. But third, a discontinuity displacement across the surface. We want that. And representation theorem is saying us, okay, you can represent it. If you write the term as an equivalent body force, you have a solution. And that's it. Now let me show it to you. And this will be the final slide for today. But let me confess to you, this is the most powerful slide, not because I'm showing it, but because this expression is used by, let's say, 100
I've not seen the slides.
Oh. So I was promising to you a beautiful view, but actually I was just looking at it. Okay. Let me tell you that in this moment, I'm pretty much sure that at least 10 seismologists are using this expression. Well, not me because I'm speaking with you and that's better, but my codes are running and they are implementing this. In Karim's team, there are at least 2 persons that are using, maybe now, this expression. Every time that you're modeling synthetic time histories due to an earthquake over extended faults or point sources, you're using this expression. So that's the beautiful view, because if you, how to say, neglect the dependencies of the quantities, you use the convolution symbol. And okay, if you do some maquillage, all that expression is this. And maybe it's worthy to remember this one. But conceptually, it's simple. It's telling that if you want to compute your signal due to some sources that are represented by a discontinuity of displacement in an elastic, maybe an isotropic body over a surface whose orientation is described by this, and you convolve it by the spatial derivative of a Green's function that is describing your body, then you're done. A final thought for you, because actually we are really on the top of the hill now. And my suggested homework for you is nothing but thinking about the next statement. Because look at the indexes. Now, what is this? This index here is referring to the 3 components of the motion at the receiver. So it's your seismogram, north-south, north-south, east-west, vertical component of motion. Nice. And this n here is here. Okay, what about the other terms? Well, remember, repeated index. So II, P, P, Q, Q, and J is here. Now look at this. That term is the Green's function. Remember, it's the solution of a problem when you have a force pointing along P. But here, and P is here you have also Q. It's a spatial derivative in the Q direction. Now, this term here actually is a couple. Is a couple with the force pointing in P and the arm pointing in Q. So you can think about this as a distribution of couples with direction in N, in P, arm in Q, and the strength is this quantity here. And it's distributed over the fault. And now, if you define this as a quantity that is called moment density tensor, then this writing is becoming this. And you should ask, final thinking for today, why density? Well, because it's something as a unit of per surface. Remember, this is an integral over the surface. And now you should ask, why moment? Uh-oh. Well, C is representing elastic parameters. So it's a force over an area. And this is a displacement. So it's a force times a displacement. It's a moment. Moment over the area. Why over area? Because you have an area here. This has no units, it's just geometry. So it's a moment density, and it's a tensor, because after the repeated index, you're left with PQ. And you can think about this as the strength of these couples. Okay. Now, that was the top of the hill, because from Monday, we'll try to survive getting down from the hill. Oh, it will be easier, because then what we will do will be the approximation of the point source. And that average will be performed. So remember, when you go to mountain, maybe the descent is always thought as easy. It's not. Because usually you don't look, okay, you walk down, but we have to concentrate because we have two issues. The first is, okay, we will get down with much smaller and shorter expressions, you will see, very easy ones, relatively easy ones. But remember that going to the hill, we have asked something to our friends at the bottom, the Green's function. Because we are using there the definition of a Green's function, but we have still to find it. So remember that we did a terrible path today with some shortcuts. We arrived to the top. Then we had been cleaning the snow, and we have seen, oh, that expression is much simpler now. And it's containing what we want. There is the idea of equivalent body forces there, a set of couples over the fault. Going down from the hill, we will see that when you move from the hill and you can say, oh, it's a point there, that set will become just a double couple. But remember that we have to return someone the Green's function because we borrowed it, we defined it, we have not found it. Okay, my friends, it's too much for today. Really, that expression is used. While we are speaking, I have two codes running, not on my laptop, but they are running also here, using that expression. Every modeler, every seismic modeler is using that expression. Every people working with inversion is using that expression for the direct computation to be compared with data. And so my decision to take with you this walk here through a very complicated topic is that because if in the future you're going to use it, you have to be an alpine guide or an Andean guide, whatever, Himalayan guide. So you need to know where the tools are. Okay? You're not a tourist. Sorry for that. So you have to be a guide. Better than me. Okay. So that's it. I know it's tough, but it's 20 years that me and Karim discussed that this concept is important because if you're going to use it, you need to know how to use it, where it's coming from, And if you need to develop it, you have to know which book and what to tune and to self-adapt it to your future needs. Okay? So, my friends, I hope that the connection today was okay. No interruptions. Okay.
Yes. Yes.
Okay, good. So,
Yeah, it was better.
okay, so my terrible house with Star Trek is better than university. Okay. The whiteboard, electronic and physical one, are still there if they are not collapsing over me under gravity. That's fine. So we will start again on Monday. We will use the knowledge acquired on the top to get a nice descent and then to make another hill for the Green's function. But let's pause for the weekend. So whatever, if you find some mistakes in the notes or whatever, please tell me. You're very welcome. And by the way, have a nice weekend.
Okay, Professor.
It will be a rainy weekend, but maybe springtime
Hello?
will come. Yes?
Yeah, hello. Yeah. I wanted to ask the host a question about the recorded video. They don't upload it on our private site that we can.
Okay,
have a
Jacobo,
private-
okay, let me tell you one thing. I've been told from the very gentle and good guy at ICTP on Monday when I was there, that wherever this lecture was occurring, from you in your rooms, me in the park, whatever, they were responsible for the recording. So I assume that they did it. They are doing it.
Yeah, it's
About the
recorded.
upload in the system, I'm not part of it. At the university, when I'm using Microsoft Teams, there is an automatic version and I do my personal action. But here, I shouldn't do it. So it's not a good response from my side, but I'm sure that they are working at it.
Yeah, there's one person joining, the host, ICTP Diploma ESP
Okay.
host. So I wanted to ask that person. Sometimes they are on, so if we are speaking, they can hear. So
yeah, I know. For example, on Monday, he was with me, and on Monday we will have a lecture for me being here. But on WED, I think I will be at ICTP, so I will ask just in case to a very gentle and efficient guy that should be here, right, in the panel. But I cannot do more than this. But if any problem is going to occur, we will do it again. And you will guide me through the representation theorem. Maybe a nice exercise could be of you explaining the representation theorem. No, I'm joking, but okay. If any problem is going to occur, we will try to fix it, okay?
Okay.
Okay.
Thank you.
So my friends, have a nice rainy weekend, and let's hope that better times will come with temperature, with the sun, and with all the additional things here. Okay.
Ciao.
Have a nice weekend in the meantime. Okay.
Ciao.
Ciao. Ciao.
Thank you.
Bye.
Bye, everyone.
Hi.